Okay, welcome everybody to the October meeting of the Amateur Astronomers Association of Princeton. And it's great to see a lot of bright young minds and very experienced club members here together tonight. Remind you, we also have, I think, around 20 or more on our Zoom session as well. So we have quite the audience for, I think, what's going to be a very enjoyable and informational and informationally rich meeting for you tonight. I want to have a few announcements I'm going to go through, and then in about 5-10 minutes, I'll turn it over to Victor, who will introduce our guest speaker for the night. And that session can go as long as it needs to go, typically an hour. We have time for a Q&A. I should point out also, I'm sure Victor will mention, but we will have a book signing that will be conducted out in the lobby outside these doors here, and the representative from the Labyrinth bookstore in Princeton is here. So here's your chance to get an autograph, to get your copy autographed. This is a rare treat. And then we'll take a break after that session while the book signing is going on. We'll come back and we'll go through some of the activities going on in the club and some really interesting things to share with you tonight. We'll try to get everybody out by 10 o'clock, so it won't be so bad. Let's see if I can advance my slides. Yes, so we have the great privilege of being here on the Princeton campus tonight. Princeton is known for many things. I'm sure you saw in what is it, U.S. World Report, Princeton ranks again as one of the top, probably #1 university in the country. Of course, that doesn't have anything to do with our influence, nor does this event, which was a big deal announced today. I imagine you heard it on National Public Radio as you were getting ready this morning. John Hopfield of Princeton has won the Nobel Prize, sharing it with a colleague from the University of Toronto, Jeffrey Hinton. And I think it's interesting to point this out because here's a person who is at the edge of the disciplines between molecular biology, neurobiology, physics, computer sciences. And this is where science is today. These are the opportunities in the future to have that interdisciplinary knowledge and training where you can hit the cutting edge, which lies between the traditional disciplines. And I think it's fascinating to realize this. Dr. Hopfield, I wish I knew him personally, I do not, but he was actually one who helped generate the early field of neural networks, which are key to what's happening in artificial intelligence. So it's a big deal here on campus. But I want to ask you guys, and now don't turn to your artificial intelligence devices, but tell me off the top of your heads, how many Nobel laureates have passed the doors at Princeton, either as faculty, as student, or associate, or visiting lecturer? How many do you think? Somebody want to guess?
We got 8
Got some guesses back here. How about you in the black coat? Say again? 50 is a good guess. On what? Ooh, closer to 50. Anybody else?
We had 8 show it. Somebody was.
Yeah, but I don't know that they're pulling up their cell phones. All right, enough suspense. I'm gonna flip it to here. I pulled this off the internet. 79. Many of them are shown here. This is Nobel laureates here at Princeton through the years. Of course, that goes back, but many of them are current. And some names we as amateur astronomers will recognize: Kip Thorne, Jim Peebles, Joseph Taylor, Russell Hulse. You can read down the list. Arno Penzias, we were talking about him at dinner, and so forth. And this doesn't include those who won the prize for economics. They wouldn't even fit on the screen. There were so many. So I just think it's worthwhile to stop and pause for a minute and realize where we are, just take in a breath and understand the magnitude of what's going on around this campus, and has for years, and hopefully will continue. And we are a tiny, tiny little atom in that universe, but I love it. So let's get a little bit more astronomical in our thinking. What's up in the sky right now? I always like to take these charts off the Sky 10, which is my favorite program for planetarium, but also for observatory functions. This program out at our observatory runs telescopes, so it's a very capable program. It has a huge database of information. And the reason I'm showing you this is that, well, we're at the time of year where the summer constellations are now drifting to the west, and you can see Cygnus. In fact, if you want to see any of the objects that are summer, early fall constellations, you better get out there pretty soon because we're rapidly migrating to the winter. But the good thing about the winter is you have Andromeda coming up. You have the greatest galaxy we can see in our skies, very visible, wonderful telescope objects. So I just make a pitch that, I think many of you know, but some of you may not have been out to the observatory we have up in Washington Crossing Park. And on Friday nights, when it's clear, we have public night, but it's also members night. You're welcome to come out. You'll learn more about that as well as directions on our website. And we have the pleasure of having our observatory chair over here running our technology, Dave Skitt, and he's basically in charge of the operations out there. So feel free to bug him at the break if you want to learn more about the observatory. I wanted to introduce a slightly different aspect of astrophotography. You know, we have a number of people in the club who are very adept at doing this, and there's an aspect that we haven't really talked about here in the club. We've done a lot of deep sky astrophotography, galaxies and nebula. We've done planetary. I'll talk about planetary later tonight. That's been one of my latest observing challenges that I've been tossing out. But there's this idea of nightscape photography where you include a landscape and use wide angle techniques to capture earthly objects in the same field as a celestial object. And so I want you to take just one quick deep gaze at the next one, and I'll explain it as I open it. This is real. Well, let me say, do you notice the crescent moon on your walk in from the parking garage? Beautiful crescent moon tonight. And just a couple of nights ago, it was a very thin sliver. My friend Laura Brandt made this photograph 3 days ago. And just stare at this for a minute. This is real. This is not artificial intelligence. This is not photoshopped. This is real. You're looking at the crescent moon behind Lady Liberty's shining beacon. And think about what goes into a photograph like this. This is real. Now, how would you do this? How could you possibly come up with the ability to do this? So I just want to give a shout out to my friend. She's not here, unfortunately. Laura Brandt is from Yardley, a real expert photographer and member of the Princeton Photo Club. Maybe some of you have been involved with that group. Here are some of the details on that shot, but I don't want to belabor this right now. I'm going to come back to it after the break and show you a little bit more how this was done. And there's a special software app that allows you to compose setups like this. You'd have a hard time doing it from paper charts and magazines and figuring out where is the angle of view where you could actually do this. So yeah, well, enough said about that. There's something else that's very dear to my heart, and that is happening this week. I'd say dear to my heart because I'm very interested in the possibility of life on other planets, and the moons in our solar system are possibly the greatest likelihood of finding any kind of life. And you're probably aware there's a big project at NASA that's getting ready to launch. In fact, the Europa Clipper project will be the first one to really get close to Jupiter's moon, Europa. A lot of facts that the AI sent to me to include on this slide. I'm not going to go through them, but a lot of reason to like Europa as a potential site where life may exist. And so the deal is that there's this hurricane down there, and you've got this very large rocket from SpaceX all ready to go, and the payload is up there, and this $10 billion project is sitting there, and here comes a hurricane. So I think there's a lot of alarm bells going off down there at Cape Canaveral. They have scrubbed, I don't know if the strike through came through. Yeah, they're striking through, obviously, the first launch day, October 10, which is Thursday. It won't happen. And everything depends on what's going to happen with the hurricane. If it gets very, very close, we could all be panicking. But we can hope for the best. And if the storm clears, then any of these upcoming days are scheduled as potential launch windows right around noon. So you want to pay attention to that. This is actually one of the biggest events going on the NASA calendar this year. And I got my fingers crossed. Yeah, so there's another observing challenge that Dave and Tom and I have been talking about behind the scenes beyond the ability to view Saturn and the south pole of the moon and the things that we've been talking about. But there is a comet out there. I'm sure you've heard about this in the news. Comet C 2023 A3. Somebody can pronounce this for me. Sushin Atlas. Did I do okay with it? So the big deal about this, you know, you're reading in the newspaper, it's the brightest comet we've seen in the decades and all this stuff. Well, it may be, but we don't know. And it's rounding the sun right now. It was impossible to see, I gather. I know they made a game try of it, but it was just too close to the sun. The glare was way too much. But as it comes away from the sun and goes back out, it in a few days is going to become an evening object at sunset. So your observing challenge that we'll talk about how to do this after the break is to try to catch a glimpse of this with binoculars, telescope, naked eye, image it, see what you can do. The problem, of course, is it's caught in the glare of the sun. And this is a chart of what the sky would look like looking west, southwest on October 16, which is next week, next Wednesday. I've sort of studied this for a while, and I think that will be the optimum time, balancing loss in the glare in the sun, separation from the sun over the days, and then, of course, diminishing magnitude of the comet. So don't take your chances. If there's a clear night, I would say from Monday on next week, go look on the western horizon, but you're going to be at a site where you have a really clear western horizon. The separation from the horizon is not great. On the 16th, it may be optimal, where at an azimuth of 251 degrees, it'll be an altitude at, I'm telling you, at exactly 7:16. So it's an hour, sorry, 7 p.m. It's 43 minutes after sunset. It will be at an elevation of 21 degrees, 22 degrees altitude. In other words, the height above the horizon. So this will be bragging rights. Anybody who can come up with it, I want to hear about it. The club wants to hear about it. We can talk about it next month. So, and finally, just to give a pitch to those of you interested in astrophotography and celestial and terrestrial capturing of data, we have an interest group that meets sort of separately from this. So it meets on the fourth Tuesday of each month and does a Zoom session to talk about technology and software and the details of the hardcore aspect of it. Welcome to join it. If you want to, you hit an email to our secretary, Gene, who's up here, and he'll get you entered into that. But it's a serious group. So, I mean, you're welcome as a beginner to join, but just understand we talk pretty hardcore language when that didn't sound right, did it? Anyway, I think I've blathered for enough time here. I'm going to turn it over to Victor, who's going to take us into the next phase. And meanwhile, I'll bring up your slides.
Tonight's talk is based on our guest speaker's latest book, The Allure of the Multiverse, Extra Dimensions, Other Worlds, and Parallel Universe. His talk he's calling The Allure of the Multiverse, Beyond the Limits of Direct Observation. Now, you might wonder why we need multiple universes instead of just one that we're learning about. Professor Halpern's talk will examine why some eminent physicists, such as the late Nobel Prize laureate Steven Weinberg, have been attracted to the idea of the multiverse, and others, such as Princeton cosmologist Paul Steinhardt, have raised significant concerns. One being, of course, whether it can even in principle be discovered, but he'll talk more about that. He'll also show how the cultural and scientific ideas of multiverses differ significantly. So a few words about our guest speaker. Paul Halpern is an acclaimed science writer and physicist. He's the author of 18 popular science books, exploring the subjects of space, time, higher dimensions, dark energy, dark matter, exoplanets, particle physics, and cosmology. He's the recipient of a Guggenheim Fellowship, Fulbright Scholarship, and an Atheneum Literary Award. He has contributed to Nature, Physics Today, Aeon, okay, Nova's The Nature of Reality Physics blog, and Forbes Starts with a Bang. He's appeared on numerous radio and television shows, including Future Quest, Science Friday, Radio Times, Coast to Coast AM, The Simpsons 20th Anniversary Special. That's the one I particularly am looking forward to trying to find somewhere. And C-SPAN's Book TV. Okay, and this is his latest book, and as Rex mentioned, we're selling them out in the lobby, and he'll be happy to sign your copy. So, Professor Halpern, thank you for joining us.
So I wanted to talk to this group who's especially his observation, astronomical observation, as to why some people in science, some people in physics are now talking about things that are not directly observable. And I want to argue that even though some things that are not directly observable might still be legitimate science. So everybody here, I'm sure, is familiar with the scientific method, where you make a prediction and then you verify the prediction experimentally. And I think everyone would agree, even supporters of the multiverse idea, that that's good science. So ideally, you make a prediction, So famously, Einstein predicted that light would bend during a solar eclipse, the starlight would bend. And this fellow here, Paul Dirac, predicted in 1928 that there would be a positive counterpart of the electron, which originally he thought was a proton, but then it turned out to be a completely unknown particle called a positron. And no one had even thought that there would be positive electrons. But then 4 years later, Carl Anderson discovered the positron. So yeah, at Caltech. So one of the few Nobel Prizes that's not from Princeton University, Carl Anderson from Caltech. So Caltech does some things too. So anyway, in astronomy, direct observation is ideal, and that's why people are so excited about the James Webb Space Telescope, looking backward in time, looking at early galaxy formation and looking at some of the oldest galaxies. So that's a way also to do direct observation. And if we could observe everything in the universe, ideally, that would be a great way to verify theories. However, even if you don't talk about the multiverse, you talk about the actual universe, we have limits. So for example, the observable universe is 46 billion light years in radius. And some of you might know that the age of the universe is about 13.8 billion years. So then you might say, well, why isn't it 13.8 billion light years? That's because the galaxies are moving away from us because the universe is expanding and accelerating its expansion. So we're seeing light from galaxies that have already moved so far away from us that they're much further out there. So we can detect galaxies that are currently beyond the bounds of observability, but we can observe them in the past. So that's why we say that the universe's observable radius is 46 billion light years. And that's a huge number, incredibly large number, but it's still a finite number. So that means that there is potentially an infinite amount of the universe, if the universe is actually infinite, that we can observe, and meaning we can never observe it. So using current telescopes of any kind, of any wavelength, there are parts of the universe that we can't observe. So we could conclude, which would be kind of silly, that there's nothing beyond the observable universe, or we can talk about the actual universe being well beyond the observable universe and saying, well, we kind of think things continue beyond it. So that's one way that scientists talk about things that are non-observable. So the theory we use in talking about the universe is Einstein's general theory of relativity, and that makes predictions far beyond observability. For example, Einstein talked about the shape of space and said, is space something that continues indefinitely, like an infinite box in all directions? Or is it something like a sphere in a higher dimension, which would be finite? Or is it something like a saddle shape? Well, if it's a saddle shape or flat, as we say, meaning like a box extending infinitely in all directions, it's going to be infinite in extent. So we can talk about the universe itself being flat, meaning extending forever, or we can say the observable universe is flat and we can't say anything beyond that. So it's a question of terminology. Do we talk about the entire universe, or do we not talk about the entire universe and only confine ourselves to things that are observable and say we're absolutely not going to ever talk about anything that's unobservable? And I think most people would say in that case that it makes sense to extrapolate and say, well, if the observable universe is flat, then it's likely that the actual universe, or at least a large part of it, is flat too, and kind of extrapolate beyond the observable. There are other things that are unobservable, but we still talk about, like the interior of a black hole's event horizon is something that's very much discussed. What happens if an astronaut enters the black hole's event horizon? What might happen to that person when they enter, in terms of their perception of time, in terms of their ability to send signals outward, which would disappear once they enter the event horizon. They wouldn't be able to send signals. Or we could just say, sorry, black hole interior, even though we can talk about it theoretically, we're not going to because it's unobservable. So I think most of us would agree that it's interesting to talk about non-observable things if we have a really good theory and if we can extrapolate from observable things to the unobservable things. So when you have something that's speculative, Hollywood is going to try to make a movie out of it and and get big bucks from speculating about things, sometimes in kind of a zany way. So some of you might remember the older ones among us that in the 1970s, after John Wheeler of Princeton coined the term black hole, popularized the term black hole, then a few years later, Disney decided to make a movie about what would happen if you entered a black hole. And it was a pretty silly movie. Black hole is kind of place where you experience kind of a judgment day, and you see like hellfire and stuff like that. It's more of a religious movie than a scientific movie, as you can see from these pictures. But still, scientists continue to talk about black holes, and it's not like scientists said, "Wow, that topic has been, exaggerated, has been mischaracterized by Hollywood, so let's not talk about it at all." Rather, they said, "Okay, ignore the movie. We're going to talk about black holes for real." So we might want to do the same with the multiverse and say, well, Hollywood's come up with movies about the multiverse, but maybe that's not exactly what science says about the multiverse. So there have been a lot of movies in recent years with fictional multiverse depictions. And if people ask, what do they have to do with science? I would say nothing at all. As I'll explain, the scientific multiverse is very different from the fictional multiverse. So there was movie Doctor Strange in the Multiverse of Madness, the Into the Spider-Verse movies with alternative versions of Spider-Man, and then the Oscar-winning film Everything, Everywhere, All at Once from a couple of years ago. So we can talk about what I call the cultural multiverse versus the scientific multiverse. So the cultural multiverse is a multiverse in movies. And we might ask, why are people so interested in the multiverse as seen culturally? And that's because we have a curiosity to know what lies beyond boundaries. So if somehow there was some barrier around Princeton and you couldn't leave Princeton, but people still talked about New York, still talked about other places, Trenton and so forth, it would become more of a mythology because you couldn't leave Princeton. But then people would still be curious, like what's happening out there. Similarly, we talk about the observable universe. We wonder what's beyond the observable universe. But even more so, we have what if questions about our lives. All of us wonder what would have happened if we made a different path, took a different path in life. So if we ended up moving to Princeton, but we had another opportunity, let's say, to move to New Brunswick for a different job, we might say, wait a minute, would I have been happier? Maybe prices would be less, or I have a bigger house or something like that. So you wonder about alternatives in life, especially in things like friendships, relationships. What if I didn't meet the person that, I ended up becoming a partner to, and so forth? These are things that appeal to people because they always wonder, what would have happened if I took a different path in life? So we also never know if our luck is good luck or bad luck. Because, for example, if you run for a train and you just make the train and you get on it, you might say, wow, I'm so lucky I made the train. But if the train immediately, hits a bump and there's an accident or something like that, then you might say, hey, maybe I should have not run for the train. Maybe I should have taken a later train. And maybe somebody who you could have met would have been on the later train. So you run for a train, you catch it, and you don't meet somebody that would have ended up being an important person in your life. So you don't know. And there's a movie, very good movie that I recommend. I have, by the way, online. If you Google it, my top 10 list of multiverse movies. It's in the journal New Scientist, and this is one of them. Sliding Doors, which came out in 1998. And in Sliding Doors, the main character just makes the subway train and just misses the subway train. So you see what happens if she catches the train and she returns home to her apartment and finds out that her boyfriend is actually cheating on her. She breaks up with him and meets someone who seems better and gets a better job and so forth. Or she just misses the train and then she gets mugged. I don't want to give too much away. And she doesn't realize that her boyfriend's cheating on her till much later. And all this stuff happens. But I don't want to give away any spoilers, but there's a big twist at the end. So watch it until the end, because you might not know which is the better path and which is the worst path until the end. So I hope I didn't give too much away. But now let's turn to science. So does it make sense to talk about the multiverse in science? Well, people do talk about the multiverse in science, but I'll argue that it's a very different idea. People are not saying in science, like, well, I can walk through that door in the back and suddenly I'm in a different universe and I'll meet someone who's like me, only evil. That's not what scientists talk about. Scientists, when they talk about the multiverse, either talk about it on the quantum level, when it's very, very subtle, or talk about it on the cosmological level. So something very small or something very large, not on the human scale. So I hope none of you are just disappointed that the scientific multiverse doesn't let you meet like versions of yourself with superpowers and so forth. So it doesn't happen. So the story of science, of scientific multiverses, happened with one of Albert Einstein's last talks here at Princeton in 1954. So he was invited by John Wheeler, who was a Princeton faculty member, to speak to his class on general relativity. And they knew each other, they were neighbors. And so Wheeler invited Einstein to give a talk to his class. And here's, we see Einstein with Yukawa, and Wheeler is on the far right. So during the talk, Einstein vented about his opposition to quantum mechanics. And those of you who follow the career of Einstein, in his later years, he often liked to diss quantum mechanics in many different ways. He liked to talk about how limited it was. Now, he believed that it was accurate, but he believed that it was limited in many ways. And one aspect that Einstein criticized was the concept of quantum measurement. So the standard view of quantum measurement, as formalized by John von Neumann, who's another Princeton faculty member, based on the philosophy of Niels Bohr of Denmark, that the quantum system is like a black box. So if you have a quantum system, you have something that you can't see inside, and you can never see inside it. But then how do you know what happens? Well, you know what happens because you take a measurement. And when you take a measurement, what happens mathematically in the process of measurement is that the system inside turns into something like a drawer in a filing cabinet with lots of dividers. And the drawer it chooses depends on the measurement. So if you're measuring the position of an electron, suddenly you have this drawer with all these dividers that are different positions and the probability of getting those positions. So you might have an electron, the chances of it being 1 nanometer to the left of a marker, 1 nanometer to the right of a marker, or directly at the marker. So you might have chances, you know, 1/3, 1/3, 1/3, for example, of it being, there's 3 different possibilities. Then once you take the measurement of position, for example, the quantum state is said to collapse into one of the possibilities. And that collapse occurs randomly, but according to the chances that quantum mechanics predicts. So there's a chance that it will go into one of the possibilities. So here we see something with 5 possibilities, and it collapses down to 1 possibility. So those might be 5 different positions, and randomly collapses to 1 position. Now, the strange thing about this, there are a lot of strange things about the standard interpretation of quantum mechanics. But one of the strange things is you can have an infinite number of possibilities. So an electron, you might not just talk about it being 1 nanometer to the left of a marker. It might be half of a nanometer, quarter of a nanometer. And in fact, you can interpret the probabilities of all different places the electron could be. So it could be very, very low probability of it being 10 nanometers from the marker. And then you have to have drawers, have dividers, let's say, corresponding to each of these things. So it becomes something called Hilbert space, which has an unlimited number of dimensions. And Hilbert also came up with an interesting analogy to talk about infinity called Hilbert's hotel, which is a hotel with an infinite number of rooms. So what would happen if you had a hotel with an infinite number of rooms? Well, let's say you saw a sign that says no vacancy. All the rooms are full. And you drive up, but you're really tired. So you go into the office of the hotel and you say, isn't there anything you can do? And they say, sure. And then they get on the loudspeaker and they say, the person in room 1, I'm sorry, you have to move to room 2. Person in room 2, move to room 3. And they move everybody 1 room over, and that clears up a room, and then you have a room. Now, let's say another person comes and they're a general and they have an infinite number of soldiers. So they have an army with an infinite number of soldiers, and they say, I demand that we all have rooms. Well, then the hotel would say, sure, no problem. And then they get on the loudspeaker again. They say, all the people in even rooms have to move to another room. So only you have to be in an odd room. So the person in room 1 can stay, but the person in room 2 has to move to room 3. The person in room 4 might have to move to the person in room 4 might have to move on to room 5, etc. So all the people in even rooms move to odd rooms, and that clears up the even rooms for the soldiers in the army. And then there's an infinite number of rooms for the soldiers. So so quantum space is a little bit similar to that. It's an infinite number of possibilities, and yet a single human experimenter, according to classical quantum, according to the standard interpretation of quantum mechanics, just makes an observation, and this infinite system collapses down to 1 possibility. Very weird. So Einstein said, isn't this ridiculous? And he said, why do you need a human observer? What about a mouse? Could a mouse observe a quantum system and trigger its collapse? Why do you need a human? And he was trying to point out the absurdity of this. So attending the lecture was a student of Wheeler, a graduate student at Princeton, who was planning to study game theory, there's a very good program of game theory here. But then he decided to switch to physics, and that's Hugh Everett III. And Hugh Everett was very stubborn, and he could be, a little bit arrogant, so he liked to stand up to professors and kind of express his own point of view. So Everett decided to come up with his own explanation. And he said, look, this idea of humans inducing quantum collapse is pretty ridiculous. I agree with Einstein. It's ridiculous. So let's come up with a system which is self-consistent. I said, well, what if collapse never happens? So all the possibilities still exist and exist forevermore. So an electron would be, 1 nanometer to the left of a marker, 1 nanometer to the right of the marker. All those possibilities exist. There's no collapse. And yet you have human observers, and the human observer would split into all the options upon the observation. So the human observer would see all the possibilities because they would suddenly become multiple people, multiple observers with only a very, very slight difference. The slight difference would be one of them would say the electron was 1 nanometer to the left. Another would say the electron was 1 nanometer to the right. A third might say it was right on the mark. So they would have different opinions, but they would never meet each other. They would just continue through life convinced that they had seen what they saw. And there'd be no other difference. So the universe would bifurcate essentially into these possibilities. So, I represent this by these observers. They're actually triplets, but I couldn't find people who split into multiple personalities. So it would happen. So Wheeler listened to Everett and thought it was a really interesting idea because his former student, who was also here at Princeton, Richard Feynman, talked about something called sum over histories, that electrons, instead of interacting just one way with each other, interact many different ways simultaneously. And that's something that became accepted in physics. And I kind of call it a multiverse in a bottle because it's like you have all these parallel universes, but you never see the parallel universes because once you take the observation, they all on a single measurement. So you need multiple paths to create a single measurement. So you don't actually see these parallel strands, but you know that they all happen because electrons interact many ways at once. And that's something that is very widely accepted because there's nothing different from observation because you just get one observation. So these bifurcation ideas are similar in some ways to a short story written around that time by Jorge Luis Borges called The Garden of Forking Paths that imagines what would happen if people encounter each other with all different possibilities in life, like two people are friends and enemies at the same time. So unlike Feynman's splitting, Everett's hypothesis imagines reality actually splitting. So instead of something happening behind the scenes, you would experience it because you would split into multiple observers. But the splitting would happen so seamlessly that you would never know. So it could be happening all the time, but you would just never know. So Niels Bohr visited Princeton. This is the theological seminary that when this photo was taken. And a whole bunch of guys met with Bohr. And the Bohr is in the center, the older gentleman. And the one to the right of Bohr is Hugh Everett. And Hugh Everett tried to convince Bohr to entertain this idea of splitting, and Bohr wouldn't even consider it because Bohr was wedded to his older idea of collapse and didn't want to take advice from a young upstart. He just wanted to, he was very famous at the time. He just wanted to continue in his ways and continue with his philosophy. So this all happened, I should say, when, well, the talk by Einstein was 1954, but by the time Everett wrote his thesis, his PhD thesis, It was not 1957. And there was a big conference at Chapel Hill in North Carolina. And Everett couldn't go to the conference, but Wheeler sent a paper to the editor of the conference proceedings, a gentleman named Professor Bryce DeWitt, who was a pretty hard-headed physicist and did, very serious calculations. And he was pretty much aghast that he got this paper for the conference proceedings that predicts the universe keeps splitting into multiple parts. And at first, he didn't even think it was worthy of publication, and was kind of surprised that Wheeler had okayed it. And the two of them, Everett and DeWitt, wrote back and forth to each other by means of Wheeler. And DeWitt said to Everett, if the universe is splitting all the time, why don't I feel it? It's not like I wake up in the morning, brush my teeth, have breakfast, and then split into, infinite numbers of parts. I don't experience that. And then Hugh Everett said, well, do we feel the Earth is turning? And yet Copernicus, said that the Earth is turning. And DeWitt said, touche, young man, you got me there. And then DeWitt became this incredible advocate of this idea. And Everett, by the 1960s, just kind of gave up on it because he never got a academic job. He went into the defense industry. He just kind of remembered the idea, but he went into a completely different career path. But DeWitt, starting in the 1960s, started popularizing the idea. And DeWitt's the one who gave it the name, the many worlds interpretation of quantum mechanics. And DeWitt published a popular article about this around 1970. And this popular article created a lot of sensations. A lot of people were like, wow, the universe splits into, infinite parts. That's amazing. And if you think back to 1969, 1970, you can imagine why people said, wow, that's groovy, man. Because that was like right after the summer of love, an age of psychedelics and things like that. So it really was kind of a hit, this idea of the universe splitting up into multiple parts. And DeWitt, got a lot of interest in the idea. And one of the people who was interested in this idea was this fellow that I have in the picture. I couldn't find a picture of him younger, but his name is Brandon Carter. He's an Australian physicist who worked at Cambridge with people like Stephen Hawking and so forth. And Brandon Carter did a lot to publicize the idea of the multiverse, but on a cosmological level. Because by that time, people started to realize by 1970 that the universe has a lot of special features. Like, for example, if gravity were stronger or gravity were weaker, then we wouldn't have planetary systems. If gravity was a lot stronger, the universe would have collapsed very early on before galaxies, stars, and planets could have developed. If gravity was a lot weaker, then you wouldn't have these structures in the universe that would just be gases. You wouldn't have things coagulating into stars and planets. And there are a lot of other coincidences in the universe, like, for example, the strength of electrical force compared to gravitational force and things like that. So there are a lot of things that make the universe favorable to life. So Brandon Carter said, he was talking about the Copernican principle. And he said, well, the Copernican principle says that Earth is nothing special, that the solar system is nothing special, that our part of the galaxy is nothing special. Well, I kind of disagree with that, Brandon Carter said. If we were in the center of the galaxy, where there's a lot more activity and you have much larger stars and so forth, we couldn't really have developed life as we know it because there'd be too much radiation. And if we were around, let's say, a red dwarf star rather than the sun, we also wouldn't have life. And he talks about in this article something called the anthropic principle, all the special things about our place in the universe that make the universe, make Earth favorable to life and intelligent. And then if we had ended up in a place, a part of the universe that's not favorable to intelligent life, we wouldn't be talking about it. So I wouldn't be speaking right now if we were on a planet where there was no possibility of intelligent life. So you wouldn't be in the audience. So the fact that we're here means that Earth has special conditions. And that Brandon Carter called the weak anthropic principle, meaning the specialness of our universe. But he also referred to many worlds and said, well, there's this many worlds idea about other universes. Maybe we can apply this to the anthropic principle and say, maybe there's a whole bunch of universes out there that have different strengths of gravity, different strengths of electricity. We can go wild with this and talk about all the different factors that could be different. And then our universe is the one among the set that can develop planets with life. So the fact that we're here not only means that we're in a special part of our universe, but we're also in a special part of the multiverse, that we're in a universe that's a favorable universe, and that all the other universes are not favorable to forming planets with life. So that attracted a lot of interest. Stephen Hawking, the late Cambridge physicist, was really interested in that idea, for example. So it became very popular. So, so we're here. So the universe does not have, super strong gravity, doesn't have super weak gravity, it has stable atomic nuclei, and even things like the creation of carbon is said to be incredibly fine-tuned. So stars can only produce carbon during late stage of collapse. And there's a process in which carbon is produced that relies on a quantum effect that is very, very special. It means that you have these helium atoms you have 3 helium atoms, and 2 of them have to combine into something that's very unstable, an unstable form of beryllium. And that is so incredibly unstable that it decays in trillionths of a second. But if it meets another helium nucleus, there is a quantum process that allows them to join up and immediately become a stable form of carbon. And suddenly what's very transitory becomes a very stable nucleus, and you get carbon. And that only happens in very, very hot conditions. So not in something like the sun, but in a collapsing star, which has to have hundreds of millions of degrees in temperature. And because of this quantum tunneling process, which is very special, then you get carbon. Well, you might ask, well, what's so special about that? Why do you need carbon? Well, to build the other higher elements, you need carbon to form the basis of even higher elements. And of course, we need carbon for life. So if things were slightly different in our universe, if you didn't have that tunneling process, then carbon would never have been created, and you'd only have lighter elements, and we wouldn't have life as we know it. So that's another example of the application of the anthropic principle. So then we sort of look forward into the 1980s, late 1970s and 1980s, when yet another application of the multiverse came up. And this was also another cosmological application. A number of scientists developed something called the inflationary theory of the universe. The inflationary theory is to explain why the universe is so smooth and so even in all directions. So if you count galaxies in all different parts of the sky, and you do account in every, every angle of the sky, the averages are pretty similar. If you look at the cosmic microwave background radiation in all parts of the sky, and you do the temperature average, it's pretty similar. So only when you sort of zoom in and look at finer structure, then you see differences. But on the largest scale, the sky is fairly similar in all directions. So the inflationary model is to explain why, if the universe started out haphazard and chaotic, how it smoothed out. And it imagines the universe undergoing a burst of ultra rapid expansion very early on in its history. So the Big Bang happens first, and then you have this burst of very, very fast expansion, which takes something from the size of less than a proton, less than an elementary particle, up to the size of a baseball. So that's an incredible difference in a fraction of a second, tiny fraction of a second, to go from something subatomic to the size of a baseball. And then that baseball size grows slowly over billions of years and eventually becomes the size of the observable universe. So there's a burst of activity and then slow growth after that. And that's a very popular theory. It's considered the standard theory of cosmology. And you might say, what causes the burst of activity? Well, there's a quantum effect that if you have a certain kind of energy field, then that causes space to blow up in that region. So it's something that you can predict. Now, we haven't found what energy field causes it, but researchers such as Andre Linde of Stanford have come up with theories. And another found inflation, Paul Steinhardt here at Princeton, also came up with theories. And both of them came to the conclusion that it's very, very easy to produce inflation, that you have a wide range of conditions for an energy field, and you can produce this ultra rapid burst, which smooths out the universe. It's kind of like stretching a sheet that has a lot of wrinkles, and you stretch it really quickly, all the wrinkles smooth out. Well, if you can get inflation really easily, then Andre Linde and others suggested, well, maybe you can have other regions of ultra rapid expansion, and that would create other bubble universes out there. So if you have one place there's ultra rapid expansion, another place ultra rapid expansion, you have these two bubbles, and they'd very quickly become disconnected from each other because they'd be expanding so quickly. So you'd have multiple universes, basically. Now, Linde of Stanford saw this as something good. He said, well, this just means that the inflationary theory is really easy to explain because you can have almost anything causing inflation. But Paul Steinhardt eventually was horrified and saw this as something really bad, because if you have a multiplicity of universes, then almost anything could happen. And you can have smooth universes, you can have very bumpy universes, you could have any kind of universe. So the question is this a predictive theory, or is it just not even science? So Paul Steinhardt has said, well, this is not even science because there's no real predictions from the theory anymore. So if you believe in inflation, most people now believe in eternal inflation, which means the existence of bubble universes. So that's why Paul Steinhardt, even though he was one of the founders of inflation, ended up coming up with alternative theories and now is one of the chief critics of inflation. So he turned against his own theory that he helped develop because he saw flaws in it. But some people believe in this idea of bubble universes, but currently the bubble universes would be so far away from ours, that we couldn't possibly reach them. They would have been inflated well beyond observation, well beyond our observable universe. But then there's a hypothesis that maybe in the creation of our bubble, and a nearby bubble, maybe our bubble collided with a nearby bubble and created a scar. And that scar would be a radiation scar. It would just be this region of hot radiation. And then over time, this region would have cooled down. But then we would see something like a ring in the sky in the cosmic microwave background that would indicate a collision with another universe. So scientists are trying to test this using data from different probes of the cosmic microwave background radiation, looking for scars of collisions. And that's research of Hiranya Pires, who looked for these rings. She found some evidence of these rings, but it was not statistically significant. So scientists looked for ironclad proof. And I interviewed her for my book, and she said, well, I don't really think we found evidence, but it's certainly worthwhile to continue to try to test this idea, because if it turns out to be true, it would be revolutionary if we can prove that there were other bubble universes that collided with ours. So she's continuing the research, but more through simulations and computational research. Now, I don't have time to go into string theory, which is this idea of energetic strands replacing particles, that instead of protons and electrons, you have these things that are like little guitar strings, and you pluck them in different ways, and that creates different masses. Very simple introduction to string theory. I don't have time to go into, the years of research in string theory. But one surprising thing about string theory is that there are many different models of what the universe would look like that support a string theory in higher dimensions. So string theory only works mathematically if you have at least 10 dimensions, which is really strange to think about. So in addition to length, width, and height, the 3 dimensions, and time, which is the 4th dimension, you'd have at least 6 more dimensions. But the question is, why don't we see these dimensions? Because they're compactified, meaning they're twisted into pretzel-like shapes that are so small that we can't detect them. Well, it turns out that the number of different pretzel-like shapes you can compactify with is 10 to the 500th power. So 1 followed by 500 zeros, which is an incredible number. So then the question is, how can you rule out all these other possibilities? Well, that's where the multiverse comes in. So this is called Calabi-Yau manifold, which is like the pretzel-like shape that the extra dimensions compactify into. And Steven Weinberg, who was a Nobel laureate, said, that multiverse idea, and others said the multiverse idea would be a way to narrow these down. And also Weinberg said there would be a bonus. And this is the last application of the multiverse I want to discuss, explaining why a factor in the universe called the cosmological constant is really, 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 really tiny, but not 0. And let me explain what the cosmological constant is. So in 1917, when Einstein developed his theory of the universe, he thought that the universe was static. He didn't realize it was expanding. So he added a fudge factor, which was a factor that constrained the universe from expanding by balancing out gravity and making the universe stable. And he called that the cosmological constant. But then when Hubble discovered that the universe is expanding, Einstein dropped the cosmological constant and called it his greatest blunder. But then in 1998, astronomers discovered that the universe is accelerating in its expansion. And they said, wait a minute, if we add the cosmological constant back in to an expanding universe, it can explain why the universe is accelerating. And you see the different models of the universe. And the top one, the red one, is an accelerating universe. It just keeps getting bigger and bigger. And that could be explained with the cosmological constant. So quantum theory also predicts a cosmological constant. based upon the energy of particles in the universe. Quantum theory predicts a large cosmological constant. Astronomy detects a small one. So the question is, why is there such a big discrepancy? And Steven Weinberg said, well, maybe there are multiple universes. Each of them has its own cosmological constant. And most of them, a cosmological constant is large. And we're just an outlier where we have a really, really tiny cosmological constant. So we're a special universe that's an oddball universe, which has a tiny cosmological constant. Therefore, with a tiny cosmological constant, gravity is the main factor until late in the universe's history. And that allows planets to form, and that allows life to form. So that explains why we're here in a universe which has a small cosmological constant. If we happen to be in a universe with a large cosmological constant, then you'd have this anti-gravity factor that would be pushing things apart, and you never have planets forming, so you wouldn't be talking about it. So that's another application of the multiverse and a kind of anthropic principle to explain why we're here. So here's bubble universes with a wide range of cosmological constants. And of that array, a tiny fraction might have a small cosmological constant, but that would be the universe that we're living in. And that would allow for gravitational clumping, resulting in stars, galaxy, planets, and life as we know. So, and you see a bunch of people excited because they're living in a universe that supports the existence of life. So something to be happy about if you're ever feeling blue. You know, be happy you're in a universe among as many in the multiverse, which has a small cosmological constant that allows for gravity to cause clumping of gases into planetary systems. Something to feel very lucky about. So in conclusion, we see that the multiverse in fiction and science are very different. Movie multiverses don't concentrate on the quantum effects or bubble universes. It would be really boring if we said, oh, I found a scar of bubble universe that we can never travel to. Or imagine, based on the quantum multiverse, imagine someone saying, I just met my doppelganger, and they think, strangely enough, that an electron that I detected a few minutes ago is actually 1 nanometer to the right of what I said. We disagree on this issue. How can we possibly get along? So it'd be kind of boring. But there are many different types of scientific multiverses out there. Many worlds, anthropic principle, eternal inflation, string theory, different cosmological constants. So it's something that some scientists believe in and some are very critical of. And for more about the multiverse, there's a lot that I left out. In fact, an infinite number of things that I left out. So you need to read the book. And luckily, by sheer chance or fate, there's a bunch of my books outside in the hallway, which after we do the Q&A section, I'd be glad to sign. I'm sold by Labyrinth Books. So be glad to take any questions. So maybe we should stop sharing the PowerPoint so people can see my face.
Or do you want to moderate the questions?
Sure. I actually have one I wanted to ask.
Well, there you go.
So philosophers of science are very big on the notion of falsifiability. And I know you talked about scars, but is there anything about the multiverse which is in principle either discoverable or falsifiable?
Well, so the scars is the big thing. And then some with the quantum multiverse, many worlds, some of the more philosophical minded people have come up with theories in which you could bet on outcomes from a quantum experiment, and that and then you see the results of the betting, and that would correspond to the branching ratios, but there really isn't a huge body of experiments to test these things. But on the other hand, believers in inflation, a lot like Andre Linde would say, well, it's clear that you have inflation. It can happen many places. So there must be multiverses out there. Just like we say, there must be something beyond the observable universe. So even that statement, there must be other bubble universes out there that are beyond observability, is something that some astrophysicists and cosmologists believe in, but it would not be directly tested.
Well, isn't the idea of the multiverse sort of based on the notion that anything that can exist does necessarily exist?
I've heard that expression, but I don't really see that with the scientific multiverse. It's more like in the quantum multiverse, in many worlds, it's more like anything that is an option for an experiment would be out there.
Mhm.
So if let's say you do an experiment with an electron and there's this wide range of results, all the results would be out there in a different universe. But to say like anything that can happen will happen, that's a little bit beyond what scientists would say.
Okay. Any other questions?
Yes?
Here, you pass that down for me?
There you go.
When these can you hear me?
I don't think it's turned on.
Hello? Okay. All right. So when these like observations happen in the different universes, and I guess the location of the different electrons gets determined in like the infinite different universes. Every time this happens, like you said, that a new universe gets created with all the different observations, like an infinite amount of universes get created with an infinite amount of different observations. Like, does this affect conservation of energy in any single way? Like, where does the energy come from? Like with new universes, or like, how does this happen, I guess?
So that's an excellent question, and the answer is that conservation of energy would not affect the creation of new universes, because it'd be a quantum effect. And just like what I talked about some of our histories, when you have all these branches of an electron happening, it's not like you have to have new energy to create these electrons. It's more like alternatives in an abstract space. So imagine an abstract space where you have all these possibilities, but you wouldn't need energy or mass to create these new spaces. They would just automatically be created. So conservation of energy would only happen within our universe. That's a good question. Yes. Yes, in the back there.
So you just mentioned about anthropic principle is the weak anthropic principle. So does that mean that there exists a strong anthropic principle?
Yes, I forgot to use that term, but the weak anthropic principle is, why are we special in our universe? So, for example, we're on the periphery of a galaxy, or the arm of a galaxy rather than the center of a galaxy, is something special. And then the strong anthropic principle is, why is our universe special among all the multiverse? So the strong anthropic principle is the one with the multiverse. The weak anthropic principle could be just a single universe.
And my another question is how does the Calabi-Yau manifold actually serves to help the string theory to explain why the dimensions why the dimensions are like twisted in our 3+1 and 3 + 1 Einstein-Minkowski time space.
Calabi-Yau manifold is something very technical. It's just the number of topological ways that you can take these large dimensions and crumple them up into small dimensions that twist them around. And I'm not a mathematician, so I know that there's tens of 500 ways, but I don't know the exact mathematical basis of it.
And
Well, is anyone else? You've had 2 questions already, so maybe we could give out someone else a chance. Yeah.
You may have already answered my question, but what my question was, if there are multiple universes, why would the different universes have different properties?
Just that would be an assumption of the theory that just that certain constants are just kind of random, and that, for example, cosmological constant that could be produced by what kind of quantum field theory, what kind of theory of particles you have, and that you might have different variations in different universes. So it's kind of like, okay, if we have a multiverse, one justification for the multiverse is to say, okay, some of these things that we think of as constants really can vary, but they don't vary in our universe, they vary across universes. So you have all these options. It's just an assumption.
Okay.
So to explain the collapse of particle wave function with multiverse, the particle is still a particle instead of being a wave function. Then if that's the thing, then how is quantum tunneling explained?
So you would still have these probability waves. So you still have quantum states, but you wouldn't have collapse. So if you're familiar with the Schrodinger equation, so the Schrodinger equation tells you if you input everything that's happening to an electron, like all the forces on the electron, it will tell you that the electron behaves like a wave in some ways, a particle in other ways, and just kind of moves through space. But then if you want to know, for example, the exact position of the electron, so if you want to know the particle-like property of the exact position, you have to take a measurement, and then you have a collapse. In the many worlds, you would still see particles, but you would see particles in all these different positions. So the quantum wave would break up into different particles in different universes, different positions of the world.
Then what about quantum tunneling? Like, how is the barrier broken? If it's the wave function, it's explained by like the wave function just goes there. But if they are just particles, then what should they do about the barrier?
Well, so that would be part of the continuous aspect. So the Schrodinger equation, you don't need to take a measurement to have tunneling. The Schrodinger equation and the idea of a wave function, you would have barrier, and you have a certain probability of being on one side and a certain probability of being on the other side. And then what would happen is, if you were to take a measurement, so in standard quantum mechanics, the orthodox quantum mechanics, you take a measurement and you have a certain tiny probability of being on one side of the barrier and another probability of being on the original side of the barrier. Well, the many worlds idea, some versions of you would see the particle crossing the barrier, and some versions of you would see it not cross the barrier. So there'll be multiple U's that would have different outcomes. Good question, Brendan.
Okay, so going back to the weak anthropic principle, how do we even talk? How do we talk about like life being like based off the conditions we know now? Because like even with like the chemistry, you were talking about forming carbon as like being very like unlikely and requiring a very specific like quantum interaction. But how do we know that life forms should be based on carbon? Like, how do we know that all these constants should be the way they should be to produce life?
So that's another excellent question. And it's true that some people speculated about silicon-based life or life that's non-carbon based and things like that. So once you allow, if you say life can be practically anything, any conditions, you don't need carbon, you don't need a sun, you don't need to be, a nice distance away from a star like the sun, then you don't have quite the specialness. So the anthropic principle kind of presumes that to create intelligent life, you need certain conditions. But you're right that it could be that there's other forms of intelligent life out there that don't need the same conditions.
All right.
Okay, so can you pass it along to over there?
Oh.
Over there?
Wait. All right, just pass it back.
I just wanted to ask, would the lack of a universe be considered a universe?
The lack of a universe?
Yeah, in the many worlds interpretation, would it still be considered as one?
Oh, the void?
Yeah.
I don't think Everett would have considered the lack of a universe.
But since it says that basically the cosmological constant could be anything, could it also be non-existent?
I mean, we're kind of delving into philosophy. But we're talking about different things because many worlds is like on a tiny scale, a quantum scale, and then cosmological constant is on a universal scale. But I think most people who, let's say, support the Weinberg view that there's all these universes with different cosmological constants would say has to be some cosmological constant in each universe. Now, there are people who are a little bit wilder, like, for instance, MIT professor Max Tegmark has talked about universes with different mathematics, like where pi is exactly 3 instead of 3.1, things like that. So, I mean, he kind of speculates about these things and written a book about that. But I kind of, in my book, kind of stick more to physics ideas.
Thank you.
Okay.
So you brought up different types of, is it working? All right. So you brought up different types of multiverses, such as the many worlds interpretation, or the bubble universes that are formed by inflation. But is there any way that they can sort of like play into each other, or is it just like one or the other?
So the anthropic principle connects a lot of them together. So the large versions of the multiverse, a lot of them are connected because people talk about eternal inflation producing bubble universes, which could have different cosmological constants, something like that, or string theory producing different types of compactification that lead to different universes with different cosmological constants that produce different bubble universes and things like that. So people connect them up. Not so much the quantum, many worlds. That's probably the least believed among scientists because there's really no evidence for it. Whereas for the cosmological multiverse, people point to eternal inflation as kind of theoretical evidence for a multiverse. So, are there any questions by Zoom? Do you know?
Okay.
Okay. So maybe we'll stop here then.
We've had some lively questions from the audience. I want to thank everybody for participating in this. I especially want to thank Paul for a fantastic talk and illuminating. I'm going to leave with one last question, if I may. We talked at the beginning tonight, I talked about the neural networks and the Nobel Prize for how it's driving artificial intelligence. So my question is, do you think as artificial intelligence finally gets there, that its it will become able to provide insight that can solve at a deeper level an understanding of the multiverse.
Well, that might be the case. I thought you were going to ask me about like the Matrix idea. That maybe like there's an AI system that's simulating
That's
our
simulating
universe.
all of this.
and that we're really simulations. So, but that's not something I really believe, because then you think if we're a simulation, then why are the creators of the simulation also simulations and stuff? But anyway, yeah, AI might certainly would be able to like help untangle things like all the variations of string theory, like go through those and test to see if they're viable or not, and maybe narrow them down a little bit. So you might narrow down a range of universes to one universe. So that would be some area where it might be successful.
Well, let's thank Dr. Paul Halpern, one of the masters of the multiverse.
Thank you. Great. Glad to enjoy it.